Okay, good morning, CCTI pre-calc students. Mr. Pashara here. I hope this finds you healthy, well, and safe. I'm thinking of all you guys at this time. It feels odd not to be in the classroom. This is the first time I put on a shirt and tie in like 2 weeks. So don't get too used to it, though. I'll be going back to my t-shirt and shorts in the rest of the lectures. But on a serious note, I hope these series of videos I will do for you guys will help you with your assignment. Your first assignment, of course, comes from section 4.4, which is exponential log equations. Very important topic. I mean, everything we do in pre-calc, of course, is important. Some of you are probably rolling your eyes right now, but it's the truth. And anybody that's going on into calc, this is a very, very vital topic. So my intentions here is to break this section down, because we cover a lot in 4.4. Exponential log equations. I'm going to do a series of videos. Today we're just going to look at the exponential equations. Please check your email about the assignment. I sent it out on Monday, and the lecture notes I sent out on the 18th of March. So make sure you double back in your emails and take a look for the lecture notes. There's like 6 or 7 pages worth of notes I sent you guys. But again, before we get started, I hope everybody's doing okay. You know, I do miss everybody, and I'm hoping that we could, get back to the classroom as soon as possible. But to get started, to solve exponential equations, you have to recall things that I taught you before the coronavirus outbreak, which is some of these properties, such as the e to the ln of x is x for all real x, ln e to the x equals x for all real x, and then ln x to the r equals r times the ln of x, provided x and r are real, but x has to be strictly greater than 0, because as you remember, logs can't take on those negative values inside. So you do have to recall these properties. These are very important for us because these are going to help us solve the equations today. And this is a very important theorem. I mean, very, very important. It says, if some number b to the u equals some number b to the v, then u equals v. So this is our roadmap to solve essentially almost any kind of exponential equation we have. What this says is, if we could get the bases to be the same, all we have to do is equate our exponents, and that's it, we're done. Game over. We got our answer. So the way I'm going to show you is pretty much the same way as the video you should have watched, or going to watch, from the textbook, with the exception that the book uses log x, common log, whereas I take the ln of both sides, the natural log. But the good news is it works out all the same. Okay, and you can check that with your calculator. You'll see that your answers match. Okay, so again, these are the properties we're going to use. And what I'm going to do here is go through some examples from the lecture notes and 1 or 2 examples from the textbook, and hopefully that will help you out here. Okay, so let's look at an example here. We want to solve an exponential equation that looks like this. So we'll start off with an easy one. So we have 2 to the 3x minus 8 equals 16. And the whole idea here is we want to use that property that says if you have b to the u equals b to the v, then u equals v. So what we got to do is we have to ask, we need to find a common base, and what is it going to be? Well, in most cases, you pick the smallest number you possibly could, and a good bet is usually the number 2 is the base that you want to use in a situation like this. So you ask yourself, how can I make this 16 look like a 2? Well, 2 to what power gives you 16? On a normal day, that would be 4. So we can rewrite this, keeping the left side the same, but making the right side a 4. So 2 to the 4. And now you see we have the same bases. So all we do now is set the exponents equal to each other. So this means we have 3x minus 8 equals 4. And you know how to do this. This is kitty stuff, right? Add 8. So you get 3x equals 12. And divide by 3. And x would be 4. So the solution set for this equation would be 4. And of course you could check it. If you put 4 back in the original equation, 3 times 4 is 12. Minus 8. 2 to the 4 is 16. So you know that you did it correctly. Okay? So this is the scenario we like to see when we can easily change the bases. Let's look at another one. How about something like this? If we have 27 to the x plus 3 power equals 9 to the x minus 1 power. So once again, we would like to be able to solve the equation by changing the base before we have to use logs or anything like that. So we look at these numbers we have. We have a 27 and we have a 9. So you have to think, what kind of base can we share amongst them? You know, we want a small number. So in other words, does 9 to some power give you 27? I don't think so. Does 27 to some power give you 9? I don't know. So we have to think a little bit smaller. So you have a 9 and a 27. A common base that usually will work out, you see these two numbers, is 3. 3 would be the common base in this case. So what we want to do is rewrite everything in terms of 3. So 3 to what power gives you 27? Well, 3 to the third power. Now, you just got to be careful. Whatever existing exponents here, you can't let it go. You can't forget it. So this is 3 raised to the 3 times the x plus 3. Okay, you see that? So 3 to the third times the existing exponent equals, now 3 to what power gives you 9? Well, that's 2, so 3 squared, and we have to multiply that by the existing x minus 1. And now you can see we have the same bases, so we go ahead and we can equate the exponents. So you take this exponent and that exponent, and you set them equal to each other. So this is going to be 3 times x plus 3 equals 2 times x minus 1. Distribute 3x plus 9 over here, and over here you got 2x minus 2. Subtract the 2x over, x plus 9 equals minus 2. Subtract the 9 over, you're going to get negative 11. So the solution for this would be x is negative 11. So, if you need to pause the video, go ahead and pause the video to look back over these two examples, but I think these two are pretty clear cut. Unfortunately, we can't always change the base. As you're going to see in the textbook, there's many times we can't change the base, so we have to use either the common log or the natural log to do so. So let's take a look at an easy example to get started. So how about something like this? 4 to the x power equals 15. 4 to the x power equals 15. So now you can clearly see, Mr. Pashar, I don't know what bases these would have in common. And you would be right. in terms of a rational number, we don't know what that is because it's not going to be a rational number that would equate both of those. So we got to go ahead and use logarithms. So the way that you can handle this is using the ln property, that if we have ln x to the r, that's r times ln x. So in your video you watched, they'll use the common log. I use the ln, but it doesn't matter. You'll get the same result in the end. So what I'm going to do is I'm going to take the ln of both sides. So I got ln of 4 to the x equals the ln of 15. Remember, ln of a number, that's just a number. So ln 15, if you go in your calculator and type in ln 15, you're going to get some kind of decimal number. It'll be a positive number. If it was an ln of some fractional number, or a number that's smaller than 1 but greater than 0, you're going to have a negative number. And again, remember, these represent exponents. So now what we do here is ln of 4 to the x is just x ln of 4, and this is just ln of 15. We want to solve for x. So we have x times ln 4. So what we're going to do here is divide both sides by the ln of 4. These cancel out. So you have x equals the ln of 15 over the ln of 4. And then this answer here is what you call your exact answer. But you could go ahead in your calculator and get a decimal answer for this. Just remember how you want to enter this. You want to say ln 15 divided by ln 4. And that'll give you a decimal answer. In the textbook assignment I gave you, the directions clearly say that when you work with these, round everything to the 100th spot. So round it to the 100th spot, and that'll be your answer. But this is a very basic example on how you use this property. You take the ln of both sides, solve for x like you normally would then. Now, the thing is, it's not always that simple. Sometimes you'll have equations that require a little bit more algebra work, and that's where your algebra skills, they really come into play with these types of things. You really got to be good on combining like terms and stuff, as you're going to see in this next example here. Okay, so next up, here's an example. We're going to have 5 to the x minus 2 power equals 4 to the 2x plus 3 power. Okay, so we have 5 to the x minus 2 equals 4 to the 2x plus 3 power. Once again, you look at this, you have a 5 and a 4 as a base. There's really nothing we can compare them with, so we're going to have to use logarithms here. We don't really have much choice. Same principle as the last problem we did, with the exception, however, you've got to be a little bit more careful because you have exponents that are binomials, meaning that you have a little bit of extra work when you have to distribute things. So let's go through it step by step. We'll start off by taking the ln of both sides. So there's your first step, take the ln. And now what we want to do is apply that property. Again, that property says ln x to the r, and I do that a lot because I write pretty heavy, is r ln x. So what that means for us is the exponents drop right down in the front. But make sure that when you do this, you put parentheses, because you're going to have to distribute this thing through, unfortunately. So at this step we have x minus 2 times ln 5 equals 2x plus 3 times ln 4. Again, again, ln5, ln4, those represent some kind of number, some kind of decimal number. So we still treat it as such when we do the algebra. That means we have to distribute the ln4 to each item in the parenthesis. So over here, you can have x ln5 minus 2 ln5 equals, over here, 2x ln4 plus 3 ln4. So it's just like regular algebra. We distribute through. Ln of a number is just some concrete number. It's not the nicest number, but it still exists, and it is still considered real, not imaginary. Now remember what your goal here is. You want to solve for x, so that means you got to get all the x's to one side. Again, you could always choose. What I'm going to do is try to keep it on the left-hand side if I could. I'm going to go ahead and subtract the 2x ln4 over. And what I'm going to do is take this constant and put it over there. Because just like in Algebra 1 when you learn to solve equations, you want the variables on one side and all the numbers on the other. So I'm going to subtract this over. So we'll do this first. So we've got x ln5 minus 2x ln4 minus 2 ln5 equals 3 ln4. And now what I'm going to do here is add this 2 ln5 over to the other side. So that means now we have x ln5 minus 2x ln4 equals 3 ln4 plus 2 ln5. Now, what do we do here? Well, these are both x terms, which is great. However, ln5 and ln4 are not like terms. So we can't just subtract this and say, oh, we got negative one of these things. They are separate entities. So do things that are kind of familiar. They both share an x, so factor the x out. So if I take an x out, I'm left with ln5 minus 2 ln4. And the right hand side I'm just rewriting as it was. Okay? And we're almost there. All we gotta do now is divide both sides by what's in the parenthesis, which is the ln5 minus 2 ln4. So I'm going to come up here and I'm going to say x is 3 ln4 plus 2 ln5 over ln5 minus 2 ln4. And this is your exact answer. Your textbook, however, will give you a decimal, which is fine. But again, you're all very capable of putting this in the calculator. 3 ln4 plus 2 ln5. Put that all in parentheses. Hit the slash or the divide button and put this in parentheses. ln5 minus 2 ln4, and that will give you some decimal approximation. So let me stand back here for a second and give you a moment to kind of compute this. So again, let's just kind of run through this. We took the ln of both sides. We dropped the exponent down in front on each side using the log property. We got the x's on one side, the ln's on the other. We had to factor out the x, which is going to be a common thing. This is going to happen all the time. Factor out the x, divide by what's left in the inside, the guts essentially, and then you have this quotient that you just simplify to get a decimal approximation. And that's pretty much how you solve it. So the interesting thing is you could, of course, go back to the very easy, the sissy problems, where you could change the base, and this will actually work for it too, but this is more work, of course. If you know how to change the base, that's what you want to do. That's the easy part. Okay? Now I want to share one problem with you from the textbook that involves E. Because when you have an E, it makes it a little bit easier to do, because E has that nice property. Remember, E has this nice property that says e to the ln of x is x, and we have ln e to the x is x. So these are very nice properties for us, and I'll give you an example where we would use such a property. So this is using base E. 0 equals 12 plus 5e to the 2x power. And this is number 33 from your textbook. This is number 33. So what's nice about this one is we have e as a base, and you're going to come to like equations that have e as a base because it works very well with the ln. Of course, to solve this, it's not in the form that we want it to be in. We don't want this 0 here because this isn't quadratic. If it was quadratic, then we'd want the 0 here. That sometimes pops up in the middle of the problem. That's a different story. So what I'm going to do here is just simply move this 12 over here, so it'll become negative. So you have negative 12 equals 5 times e to the 2x. Now go about your normal business. This is 5 times e, so this is a number. We can divide 5 on both sides to get negative 12 fifths equals e to the 2x. There's one thing I want to mention here. There's a typo here. I think this should be a negative 12, but we're just going to roll with this so I can show you what happens, because something actually very interesting happens here. So in the book this would be a minus, so that would come over as a plus, but I'm kind of glad I made this mistake so you can see what happens here. At this step you would take the ln of both sides, and when you do that, over here on this side, ln to e to the 2x is just going to be 2x. So whenever you have ln e to an exponent, that exponent just comes down, and guess what? This e is totally gone. But because of my mistake that I made here, something interesting happens over here. ln of negative 12 fifths. Now, do you remember about what numbers ln's cannot take on? I hope you're saying negative, because they can't take on negatives. So based on this, we can't take the ln of negative 12 fifths. So this equation can't be solved, right? There's no solution to this. So there's no solution because you can't take the natural log of a negative number. If I haven't made a mistake, this would have been the ln of 12 fifths, and you would just have ln 12 fifths equals 2x, divide both sides by 2, and you'd be able to get your boring decimal. But I think this, because of my silly mistake here of writing this incorrectly, I think this goes to show you what can happen. So be on the lookout for a situation like that. Okay, I think we covered the basics here to get you started. So I hope this video finds you well, and I hope this has been helpful for you. I will post this on YouTube, of course. I'll send out the email where to find it. But again, I hope you're all doing well. I do miss you. Hope that we get back in the classroom sooner than later. Remember, I have office hours Monday through Friday from 11 a.m. to 1 p.m. So if you have any questions on the material, feel free to email, call, whatever, and I'll try to help you the best I can. Please read the textbook. Please watch the videos I sent, and we'll have some upcoming videos on solving log equations. So until then, CCTI pre-calc periods 1 and 2, be safe, and I'll see you when I see you.